We introduce a new pipeline for learning articulated rigid body simulations from depth and RGB video. Setting up a physics engine is a laborious task. One has to define the robot model, commonly in the URDF format, which defines the joints between the robot links and other kinematic properties, as well as parameters for the inertia of the bodies in the scene, among many other simulation settings. It often requires a lot of trial and error between data collection on the real robot and then manually tuning the simulator to achieve acceptable simulation accuracy. When we want to calibrate a physics engine to the real world, we typically collect proprioceptive measurements or use a motion capture system to obtain low-dimensional state information. While such careful data collection simplifies the system identification problem, it requires laborious instrumentation of the environment. In this work, we aim to find a simulation directly from pixel-based observations. Given a sequence of RGB or depth images, we find the rigid bodies in the scene, identify the joints connecting them, and learn the dynamics parameters, such that we achieve an accurate simulation of the real mechanism. In the first step of our pipeline, we find the rigid bodies in the first frame of the video. We assume the objects in the scene are known and train a Detectron 2 instance segmentation network from our own dataset of rigid body arrangements. To obtain 3D meshes for simulation, we scan the parts via a desktop 3D scanner. Having identified the objects in the scene, we track their motion in the image sequence via an inverse rendering approach. We set up the objects and a camera in the differentiable rasterizer NV-diff-rast. For each frame of the video, we optimize the poses of the rigid bodies such that the pixel-based loss between the rendered and real image is minimized. To ease the optimization, we run it from different randomized initial pose configurations based on the best guess from the poses of the previous frame. Now that we have the 3D motion of the rigid links of the mechanism in the video, we aim to reconstruct the articulation of the system, i.e., how the links are connected. In order to identify the joints, we consider the relative motion between two bodies at each frame. Now, we estimate the parameters of three possible joint types. First, for a prismatic joint, the axis is the normalized difference in translation. Second, for a revolute joint, we find the axis and pivot point through these equations. Finally, in case of a static joint, the relative transform between the two bodies is the same at every frame. Given the parameter estimates for each joint model at each frame, we leverage random sample consensus, or RANSAC, to reject outliers while finding the best fitting joint model. The joint candidate with the lowest model error is memorized in a cost matrix. To select the most likely articulation of the entire mechanism, we need to find the correct joint topology over this cost matrix. Let's consider a coupled pendulum system where the link on the left is attached statically to its parent and the link on the right is connected via a revolute joint. Given the previous steps of our inference pipeline, we found the following cost matrix. To determine the articulations of the systems, we find the minimum spanning trees. In our example, body 1 and 2 have been correctly determined to be children of body 0 connected via a static and revolute joint, respectively. Finally, we need to infer how the root body 0 is connected to the world frame. Again, we run RANSAC on our three joint models, and if the error of the best model is below a certain threshold, the system is determined fixed base. Otherwise, the system has to be simulated as a floating base mechanism. In our example, body 0 is attached to the world frame via a revolute joint which completes the articulation inference step. Having determined the joint topology of the mechanism, we now need to infer the dynamical properties so that our inferred simulation is an accurate digital twin of the real system. We employ a differentiable simulator as dynamics model in conjunction with the differentiable rasterizer NV-diff-rast to allow us to calculate gradients of the simulation parameters with respect to a pixel-based loss function. We leverage a Bayesian inference method we introduced earlier, named Constrained Stein Variational Gradient Descent, or CSVGD, to approximate particle distributions over parameters, such as the masses and inertial properties of the rigid bodies in the system. Here we show the overall Video2Sim pipeline, which starts with an RGB or depth image sequence as input, identifies the objects in the video, tracks them in 3D, infers the mechanism's articulation and estimates the simulation parameters to yield a highly realistic physics model of the real system. In our first experiment, we infer the articulation of the mechanism consisting of two revolute and two static joints. Next, we find a physics model for a Cartpole simulated in the Bullet physics engine from which we recorded a depth video. Our simulation is accurate enough that we can use it as a dynamics model in a model predictive controller that achieves a swing-up motion with performance closely approaching the cost under the true dynamics model. Given an RGB video of a coupled pendulum mechanism, we are able to recover the articulation and simulation parameters and initial conditions that allow our simulated model to closely follow the motion of the real observed system. Finally, we investigate a scenario where a robot arm pushes a planar mechanism via a cylindrical tip. Given a depth image sequence, we infer an articulation model that closely matches the true arrangement of the two revolute joints. Thank you for your attention.